Got it. For a proper solar installation, whether small scale, home office, or larger projects, certain tools are essential to make the work efficient, safe, and professional. Let me break it down into categories with descriptions. Basic hand tools. 1. Screwdrivers, flathead and Phillips. Used for tightening, loosening screws on panels, junction boxes, and inverters. 2. Spanners and wrenches for fastening panel frames, mounting structures, and inverter bolts. 3. Pliers, combination, long nose and cutting pliers. Used to bend, hold, twist and cut wires during wiring connections. 4. Hammer and drill machine hammer for mounting work, drill for making holes in walls, poles or rooftops for cable routing and mounting structures. 5. Measuring tape and marker ensures proper alignment, spacing, and neat finishing during installation. Electrical tools. 6. Multimeter, digital analog, measures voltage, current, and resistance to test solar panels, batteries, and inverter outputs. 7. Clamp meter, for measuring current flow without disconnecting wires, useful for live system checks. 8. Insulation tester, Megger, ensures insulation safety and prevents leakage current in wires. 9. Crimping tool and cable lugs, for making solid cable terminations to batteries, inverters, and panels. 10. Wire stripper and cable cutter, used to strip insulation and cut solar cables neatly without damage. Mounting and safety tools. 11. Spirit level ensures solar panels are properly leveled and aligned for maximum sunlight capture. 12. Spanners socket set for tightening mounting bolts and nuts. 13. Safety gear, gloves, helmet, safety shoes, goggles, harness. Protects installers from electrical shocks, falls, and injuries. 14. Ladder, scaffolding needed for roof installations and high mounting structures. Specialized solar tools. 15. MC4 connector tool, specifically for tightening, loosening, MC4 solar connectors used in panel wiring. 16. Solar irradiance meter, measures sunlight intensity at the installation site to determine best panel positioning. 17. Battery hydrometer, for lead-acid batteries, measures electrolyte level and specific gravity in batteries. 18. Torque wrench, ensures bolts and nuts are tightened with the correct torque to avoid over-tightening or loosening. Other essentials. 19. Cable ties and clips, for organizing and securing cables neatly. 20. Conduits and trunking, tools for routing and protecting cables against weather or mechanical damage. 21. Labeling machine, tape to label wires, breakers, and components for easy maintenance later. With these tools, a solar installer can carry out panel mounting, electrical wiring, inverter connection, and system testing in a professional and safe manner. Solar site inspection procedure. 1. Preparation before inspection review, project design documents, load requirements, and client requests. Gather inspection tools, tape measure, compass, shock clinometer, solar pathfinder or mobile app, multimeter, camera, notebook tablet, PPE, helmet, gloves, safety boots. Schedule inspection with client and ensure access to all relevant areas, roof, ground, electrical rooms. 2. Site assessment. A. Location and accessibility. Confirm site address and GPS coordinates. Assess accessibility for installation vehicles, equipment, and future maintenance. Check for safety hazards, unstable roofs, restricted areas, overhead lines. B. Roof, ground condition. Inspect roof type, material, and structural strength. Timber, concrete, metal. Measure tilt, angle, and orientation, azimuth. For ground-mounted systems, assess soil type, shading, and land leveling requirements. 3. Solar resource and shading analysis. Measure roof, ground azimuth and tilt using compass, clinometer. Use a solar pathfinder, drone, or mobile app to identify shading obstacles, trees, buildings, poles, antennas. Take photographs of shading conditions at different times of the day. Record solar irradiance data if available. 4. Electrical assessment. Locate main distribution board, sub-panels, and inverter installation points. Record Record available breaker spaces and rating of existing electrical system. Measure voltage levels, single phase or three phase. Inspect grounding, earthing system. Check proximity of installation area to electrical connection point to minimize cabling. 5. Structural and mounting feasibility. Determine available area for panel installation, roof surface or ground space. Check roof age, strength, and warranty. Identify obstructions, vents, skylights, AC units, satellite dishes. Assess possibility of mounting system, flush mount, tilt mount, ground mount, carport. 6. Safety and environmental considerations. Identify fire hazards or flammable materials near installation area. Check wind exposure and stormwater drainage. Ensure compliance with local building codes and electrical regulations. Note space for battery storage, if hybrid or off-grid system. Assess accessibility for maintenance. 7. Documentation and reporting. Take detailed photos of roof, electrical panels, shading obstructions, and possible inverter, battery locations. Draw a simple site layout sketch with measurements. Record all technical data. Roof tilt, azimuth, available area, shading analysis results, electrical capacity. Prepare a site inspection report summarizing findings, recommendations, and potential constraints. 8. Client discussion. Share observations with client, roof condition, shading issues, electrical upgrades if needed. Discuss possible system size, inverter, battery placement, and installation timeline. Highlight any structural reinforcements or upgrades required. System summary. Inverters. 2x5 kVA hybrid inverters configured in parallel. Combined capacity 10 kVA. PV array. 22x400W mono panels, 5.28 kWp total, with 60% efficiency. Topology. PV strings in series parallel into MPPTs. Shared DC bus. Inverters paralleled on DC and AC sides per manufacturer instructions. Optional, if applicable. 48V battery bank on the common DC bus. Grid generator as AC input source. Expected daily production from 5.28 is typically 26.1 kWh, depending on site irradiance, tilt orientation, and seasonal factors. A. PV field design, 22x400W module assumptions, typical 400W mono, verify with actual datasheet. VMP 35 to 36, V, BABIC 46 to 47V, IMP 9.510A, ISC 1011A. Because MPPT input voltage windows differ by inverter model, choose one of these safe common layouts. Option 1. High voltage MPPT, e.g. 120 450 VDC 18A per tracker. Stringing, 2 strings of 7 modules in series, 7S, or 14 and 8s, or 22 modules. 7X, VMP 7X 41, 287 VMP, ideal range for 120, 450 V trackers. 7X, Vox 7X 49, 343 VOC, well below 450 V, even in cool mornings. Parallel, 2 strings in parallel, TUC 7S into the MPPT combiner. Pros, voltage sits nicely in the efficient MPPT zone with modest parallel current. Cons, all 22 modules. Pick an option that matches your inverter MPPT spec. If your tracker allows PUDUA50 450V, that's create, but always check the nameplate of your inverter before doing panels configuration. Combiner and protection for either option. String fusing, 15 string fuses, or per module ISC X125X 1.25. DC SPD Type 2, add combiner and add inverter if cable run, 10-15 mM. Isolator, lockable DC isolator near inverters. Earthing, PV frame array bonded to site earth, surge earth with atténuant target if practical. Cabling, UV-resistant PV cable, 10 mm per voltage drop in current. MC4 connectors, tidy cable management. Mechanical mounting rails, mid-end clamps, torque per manufacturer. Wind and corrosion rated hardware. Tilt or 10 M15 to grain or site optimal. Azimuth as close to due south in Nigeria as roof allows. Even row spacing to avoid self-shading. B. Inverter configuration, parallel. 1. Mountain clearances. Fix both 5 kVA units vertically on a ventilated wall, clear of moisture heat sources. Respect side, top-bottom clearance. 2. DC bus, battery Shomart hybrid. If using batteries, common 48V bank size to load profile, e.g. 48V, 200, 400 AON usable depending on autonomy target. Each inverter connects to the shared DC bus through its own DC breaker, e.g. 125A200A at 63 VDC, plus DC SPD Type 2. 3. PV inputs, LAN combiner outputs on the inverter, MPPTs. Some 5 kVA units have dual MPPTs, split strings evenly per MPPT if available. 4. Parallel sync, install the manufacturer's parallel communication kit, CAN RS485 parallel sync leads. Set one unit as master, the other as slave, matching firmware versions and settings. 5. AC input, grid gen. Bring grid generator feed to the AC in terminals of both inverters via a common upstream breaker and individual AC input breakers. Fit AC SPD Type 2 on outgoing supply, neutral earth bonding per inverter manual. 6. AC output, essential loads board. Paralleled AC out from both inverters to a dedicated essential loads DB via an output isolator and appropriate MCBs, share RCBOs for circuits. Non-essential loads remain on the main DB or through an ATS ESS logic if specified. Earthing and neutral, follow inverter manual for NE bonding in backup mode. Some units switch neutral internally, others require an external NE link via an ATS relay. Ensure a single point of NE bond to avoid loops. Verify RCD operation on the essential board. See protections and sizing guidance. DC side, battery bus. Cable size to limit voltage drop. 2 to 3% at peak current. For 5 kVA 48V, full load DC current per inverter, 5000 VA, 48 VXE, 105, 115A, year 995. Size conductors and breakers accordingly. AC side, combined output 10 kVA at 230V, 43A max. Size output isolator and sub-dB accordingly, e.g. 63A main with branch RCBOs. Surge, Type 2 SPDs on PV, DC bus, and AC in, out. Add Type 1+2 on service entrance if the site is lightning prone. Isolation, clear lockable AC and DC isolators adjacent to equipment. D, controls and settings. Parallel mode, enable per manual. Confirm current sharing is active. Battery type and limits. Program BMS protocol or absorb float voltages. Set charge. Discharge current limits to protect battery. PV priority, typically PV, load, battery, grid, gen, but set to client preference. Grid, gen parameters. Input voltage, frequency windows, genset start logic, if used. Load scheduling, time of use, peak shaving, or quiet hours if supported. E. Testing and commissioning checklist. 1. Pre-power checks. Torque on all lugs, polarity on every string, insulation resistance, PV plus to earth, PV to earth, continuity of earth. 2. Power up order. Battery DC on, inverter idle, PV isolator on, AC input on, if used. 3. PV verification. Each string, VOC C, measured versus datasheet temperature corrected values, MPPTs tracking correctly. 4. Parallel sync. Confirm both inverters synchronize, L8 HMI, equal load sharing at several load points. 5. AC tests. Phase, neutral correctness, RCD trip tests, voltage drop under load, ATSMR transfer behavior, if applicable. 6. Alarms harness logs. Verify no active faults. Confirm data logging, monitoring, Wi-Fi, RS485 cloud app. 7. Handover. Provide single line diagram, as-built string map, passwords, O&M guide, and warranty papers. F. Bill of materials, indicative. 2x5 kVA hybrid inverters, parallel capable. Plus parallel kit, cables. 22x400 WPV modules. Plus mounting kit, rails, clamps, fasteners. PV combiner box with string fuses, DC isolator, DC SPD Type 2. DC battery breakers, shock fuses, DC SPD, DC isolators, AC input-output breakers, essential loads, DB, AC SPDs, UV-rated PV cable, 4.6 mm, DC battery cable, e.g. 35 to 70 nm per calc, AC cables, lugs, MC4s, conduits trunking, earth rods and clamps, labels, harness signage monitoring dongle, logger, if not integrated, G, single line diagram, narrative, PV strings, PV combiner, fuses plus SPD plus isolator, inverter MPPTs, DC bus with battery via DC breaker and SPD, inverters in parallel, AC output isolator, Essential loads DB with RCBOs, loads. Grid generator, AC input of both inverters through upstream protection and SPD, provides charging bypass as configured. Notes and assumptions to verify, confirm actual MPPT voltage window to select option 1 or 2 stringing, confirm module VOC VMP, and apply cold temperature VOC correction before fixing string count. Confirm battery chemistry and capacity, if any, to set charge limits. Ensure local code compliance, i.e. CBS NEC as applicable, and utility interconnection rules.